Right now, as you are watching this, the Pacific Ocean is changing in two different ways at the same time. Across the tropical Pacific, El Niño has officially formed and is strengthening faster than it was only a few weeks ago. Farther north, two large marine heat waves are already sitting across the northeast Pacific, including one that has persisted near California since May of last year and another expanding far offshore. On July 9th, NOAA reported that the central tropical Pacific had warmed to about 1.2 degrees Celsius, above its updated average, while waters closer to South America were running as much as 2.7 degrees above average. One day later, NOAA's West Coast heatwave tracker confirmed that parts of the ocean off California were among the warmest ever observed for this time of year. This does not mean a superstorm is guaranteed. It does not mean the Pacific has suddenly become uncontrollable. But it does mean the ocean atmosphere system has entered a more strongly coupled warm phase, and the United States may begin feeling the consequences through tropical storms, coastal flooding, changing fisheries, shifting rainfall, and a reorganized winter jet stream. Today, we are going to break down exactly what is going on, where it is most dangerous, and whether things could get even worse. No guessing, no dramatizing, just the facts, the science, and the real stakes. Drop a comment right now. Have you ever personally experienced an El Niño winter, a damaging Pacific storm, unusual coastal flooding, or ocean water that felt far warmer than normal? Tell me where you were and what happened. If you want to be the first to know every time something major changes in the oceans, atmosphere, or climate system, subscribe. It is completely free. A thumbs up also helps enormously. Let us go for 5,000 likes on this one, so the algorithm actually shows it to people who need to see it. Now let us get into it. The story did not begin with a single dramatic satellite image. It developed slowly, over more than a year, across thousands of miles of ocean. In May of 2025, researchers began tracking a large area of abnormally warm water near the central and southern California coast. They named it NEP-25A, meaning the first large Northeast Pacific marine heatwave identified in 2025. By September, that heatwave had expanded and intensified enough to rival the enormous warm water event remembered as the Blob. On September 9th, the average surface temperature across the Northeast Pacific reached 20.6 degrees Celsius, roughly 69 degrees Fahrenheit. NOAA scientists describe that as the highest regional average measured in the modern record, nearly half a degree Celsius warmer than the previous record. That may not sound dramatic on land, where temperatures can change by 10 or 20 degrees in a few hours. In the ocean, however, a regional average shift of even 1 degree can represent an extraordinary amount of stored energy because water is dense, deep, and difficult to heat. During October and November, the warm area contracted, following a seasonal pattern scientists have seen in many recent marine heat waves. That could have been the end of the story. Instead, the pattern changed. In December, the warm region expanded again along the southern California coast. It then remained in near-shore waters through the winter and into the summer of 2026. That persistence mattered. A short pulse of warmth may disrupt local conditions for days or weeks. A warm anomaly that survives across seasons can affect feeding cycles, migration routes, nutrient availability, spawning conditions, and the timing of biological events over a much longer period. Then a second large heat wave appeared. In May of 2026, NOAA's tracker identified NEP-26A far offshore, generally between 37 and 47 degrees north latitude. That places the core of the feature west of the United States and Canada across the open North Pacific. During June and early July, it expanded. These offshore heat waves often grow through summer. Some remain far from land. Others move closer to the coast when winds weaken, pressure patterns change, or coastal upwelling relaxes. That is one of the first signals scientists are watching closely. Not simply how hot the water becomes, but whether the warm pool moves into the coastal zone where fisheries, beaches, ports, marine mammals, and coastal communities are directly exposed. At the same time, a second process was developing along the equator. During the winter of 2025 into 2026, the tropical Pacific had been influenced by weak La Niña conditions, the cool phase of the El Niño Southern Oscillation. By spring, those colder conditions were fading. Warm water below the surface began moving eastward in the form of a downwelling Kelvin wave. This is not a breaking wave like the kind that reaches a beach. It is a broad, slow pulse in the upper ocean that deepens the boundary between warm surface water and colder deep water. As that pulse travels east, it can suppress the normal rise of cold water and allow surface temperatures to climb. By June 11th, NOAA had enough evidence from both the ocean and atmosphere to declare that El Niño had formed. The declaration was based on more than a red patch on a sea surface map. Scientists were watching sea temperatures, subsurface heat, trade winds, cloud patterns, air pressure, and tropical rainfall. The warmer water had moved into the central and eastern equatorial Pacific. Low-level winds were showing westerly anomalies, meaning they were weaker than normal or locally blowing opposite the usual trade wind direction. Thunderstorm activity was increasing over parts of the central Pacific and decreasing near Indonesia. The ocean was not warming alone. The atmosphere was responding. That coupling is the real threshold. The Pacific can experience temporary warm water without producing a full El Niño. El Niño becomes established when the ocean and atmosphere begin reinforcing each other. Weaker trade winds allow more warm water to shift east. The warmer water changes where tropical thunderstorms form. Those thunderstorms release enormous quantities of heat into the atmosphere. That changes pressure and wind patterns, which can weaken the trade winds further. The system becomes a feedback loop. The July 9th update showed that this loop had strengthened. The weekly Niño 3.4 value, measured across a large central equatorial region used to monitor El Niño, reached plus 1.2 degrees Celsius using NOAA's relative index. The eastern Niño 1+2 region was at plus 2.7 degrees. Subsurface temperatures had risen. The thermocline had deepened in the east. Atmospheric pressure indicators were strongly negative, another sign that the tropical circulation had reorganized. NOAA concluded that El Niño was continuing and would strengthen through the end of the year. Forecasters assigned a 97% chance that it would persist through early spring of 2027. They also placed the probability of a very strong event during October through December at 81%. That changed fast. Only a few months earlier, the Pacific was emerging from a weak cool phase. Now forecasters were discussing the possibility of an event that could rank among the strongest in records going back to 1950. But here is the part that must remain clear. A very strong El Niño is a measure of the tropical Pacific's temperature and atmospheric response. It is not a prediction that every typical impact will happen in every location. The strongest El Niño can fail to deliver heavy rain to one part of California while producing flooding in another. It can suppress overall Atlantic hurricane activity while one destructive Atlantic storm still forms. It can create a stormier southern United States without making every week wet. Climate patterns tilt probabilities. They do not write a fixed daily forecast months in advance. The most unusual element in 2026 is not El Niño by itself. The Pacific has produced El Niño events for centuries. It is the overlap between a strengthening tropical El Niño and persistent marine heat waves in the Northeast Pacific. NOAA is tracking two warm regions that are not currently caused by El Niño. The California coastal heat wave began before El Niño formed, and the offshore heat wave has its own atmospheric and oceanic drivers. Scientists have specifically warned against simply adding their temperature anomalies together as though two warm systems automatically create one giant super event. Ocean dynamics are more complicated than that. Coastal winds can pull cold water upward. Storms can mix heat downward. Currents can move warm water away. Clouds can reduce incoming sunlight. One pattern may weaken another in a particular location. The deeper concern is duration. California's coastal zone may move from heatwave-driven warmth directly into El Niño-related warmth during fall and winter. In other words, the source of the anomaly may change while the ecosystem receives little recovery time. NOAA researchers have compared the setup to 2015, when the blob was followed by one of the strongest El Niño events on record. The current event is not yet identical to that period. The recent marine heat wave is smaller in important ways, and strong coastal upwelling has kept waters off northern California, Oregon, and Washington cooler than normal during parts of the summer. Still, the sequence is familiar enough that scientists are checking the data again and again. To understand why this matters beyond the ocean, we need to look at the Pacific as an engine, not a background. The Pacific is the largest ocean on Earth. It stores heat, transports moisture, and helps organize global atmospheric circulation. When a region spanning millions of square miles warms, the change does not stay neatly inside that patch of water. Heat changes evaporation. Evaporation changes humidity. Humidity changes cloud formation and rainfall. Tropical rainfall releases latent heat, which alters air pressure high above the the ocean. Those pressure changes can launch wave-like patterns through the atmosphere, influencing the jet stream thousands of miles away. The normal tropical Pacific has a strong east-to-west temperature contrast. Trade winds push warm surface water toward Indonesia and the western Pacific, where the warm layer becomes deep. Near South America, colder water rises from below, helping maintain a cooler eastern Pacific. Air rises over the warm western ocean, flows eastward at high altitude, sinks over the cooler east, and returns westward near the surface. This enormous circulation is called the Walker circulation. During El Niño, that system weakens or shifts. The trade winds relax, warm water spreads east. The zone of strongest thunderstorms moves toward the central or eastern Pacific. The location of rising tropical air changes and the entire global circulation adjusts. One of the most important U.S. responses often appears in the North Pacific jet stream. During a typical El Niño winter, the jet stream tends to extend farther east and shift southward. That can guide more storms across the southern tier of the United States. It can favor wetter conditions from Southern California across parts of the Southwest, Gulf Coast, and Southeast. It often supports warmer conditions across the northern United States and drier conditions in parts of the northern Rockies and the Ohio and Tennessee valleys. But the word typical is doing a great deal of work. The jet stream is affected by other patterns, including the Arctic Oscillation, the Madden-Julian Oscillation, the Pacific Decadal Oscillation, sea ice, snow cover, stratospheric winds, and short-term weather systems. El Niño loads the dice. It does not control every roll. This is why responsible forecasters speak in probabilities rather than certainties. Marine heat waves work differently. A marine heat wave is defined relative to the local climate at that place and time of year. Water is considered in heat wave status when temperatures remain in the warmest range of the historical distribution for at least several days. A surface anomaly of 3 degrees Fahrenheit may be moderate in one location and extraordinary in another, depending on the season and local variability. The Northeast Pacific heat waves are tracked through satellite data, ships, and buoys on a grid that allows researchers to follow contiguous warm areas almost like meteorologists track storms. Off the west coast, one of the strongest defenses against marine heat is upwelling. When winds blow from north to south along the coastline, the rotation of Earth helps push surface water away from shore. Cold, nutrient-rich water rises from depth to replace it. This process supports one of the world's most productive marine ecosystems. It feeds plankton, which supports small fish, salmon, seabirds, whales, and commercial fisheries. When the winds weaken or reverse, upwelling can slow. The surface warms. If a large offshore heat wave is already nearby, the warm water can press toward the coast. That is why the same regional map can show cool water near Oregon and Washington, while much warmer water sits offshore or farther south. It is not a contradiction. It is the result of winds, coastline geometry, currents, and ocean depth operating at different scales. Scientists are watching whether the cool coastal strip holds. If upwelling remains strong, it may protect portions of the ecosystem. If it weakens for an extended period, the warm offshore water may reach areas that have so far escaped the worst anomaly. To put the energy in context, heating a thin surface layer of ocean across a huge region requires more energy than heating the air above it by the same number of degrees. Water can store roughly 4 times as much heat per unit of mass as air, and the ocean contains far more mass. That stored heat does not automatically become a hurricane or a California rainstorm. Much of it may remain in the water or be moved by currents, but when atmospheric conditions allow, warm water provides moisture and energy that storms can use. That connection is especially important in the eastern and central Pacific hurricane basins. NOAA's 2026 outlook gives the eastern Pacific a 70% chance of an above-normal season. The forecast range includes 15 to 22 named storms, 9 to 14 hurricanes, and 5 to 9 major hurricanes. Accumulated cyclone energy, a measure combining storm strength and duration, is forecast at 120 to 190% of the median. In the Central Pacific, which includes water surrounding Hawaii, NOAA projects 5 to 13 tropical depressions or named storms, also favoring an above-normal season. Those numbers do not mean 9 major hurricanes will hit the United States. NOAA does not issue seasonal landfall predictions because storm tracks depend on shorter-term steering patterns that cannot be known months in advance. Many eastern Pacific hurricanes curve west into open water or weaken near Mexico. Some send moisture into the southwestern United States without making landfall. Others create dangerous surf, rip currents, or flooding hundreds of miles from their centers. Hawaii's risk also depends on where storms form and how the subtropical ridge steers them. The seasonal signal raises the background potential. Individual threats still require day-by-day forecasts. The contrast with the Atlantic is striking. NOAA currently favors a below-normal Atlantic season, partly because El Niño tends to strengthen upper-level winds over the Caribbean and tropical Atlantic. Those winds create vertical shear, which can tilt or disrupt developing storms. The Atlantic outlook calls for 8 to 14 named storms, 3 to 6 hurricanes, and 1 to 3 major hurricanes. But here again, below normal does not mean safe. One landfalling hurricane can create a catastrophic year for a community, even if the basin produces fewer total storms. The Pacific's new phase may also reach American shorelines without a tropical cyclone. El Niño can raise sea levels along the west coast. Weaker trade winds and eastward-moving Kelvin waves deepen the warm upper layer and can push elevated water toward North and South America. Warm water also expands. When the average sea level is already elevated, ordinary high tides begin from a higher starting point. Add strong surf, low atmospheric pressure, storm surge, or a king tide, and water can travel farther inland. NOAA has described this as a possible double whammy. The first factor is long-term sea level rise, which has already increased the frequency of high tide flooding in many coastal cities. The second is a strong El Niño that can temporarily raise water levels and reorganize storm tracks. The result may be more frequent, deeper, or more widespread coastal flooding along parts of the west coast. The atmospheric shift can also direct storms toward the mid-Atlantic and increase heavy rain potential along parts of the Gulf and Southeast. That does not mean both coasts will flood continuously. It means the threshold for nuisance or damaging flooding may be crossed more easily when tides and storms line up. The human stakes are easier to understand when we look back at the blob and the 2015 to 2016 El Niño. The blob began as a vast region of warm water in the northeast Pacific. It altered the food web, pushed species outside their normal ranges, and contributed to one of the largest harmful algal blooms recorded along the west coast. Fisheries closed, marine mammals struggled, seabirds died in large numbers, warm water species appeared far north of their usual habitats. Salmon entering the ocean encountered prey with less energy, reducing survival and contributing to weak returns in later years. For fishing communities, these changes were not abstract climate statistics. Boats traveled farther. Processing plants lost supply. Managers closed seasons to protect depleted stocks. Families that had built their incomes around salmon, sardines, crab, or other species faced uncertainty. Some industries found temporary opportunities. Market squid shifted north, producing new landings in Oregon. Rockfish juveniles increased in some areas. Ocean change creates winners as well as losers. But the transition can be chaotic because infrastructure, regulations, and local knowledge are built around historical patterns. Warm water can also compress habitat. Along the west coast, cool, upwelled water creates productive feeding corridors close to shore. When offshore heat presses against that narrow, cool zone, whales, anchovies, fishing boats, and crab traps may be forced into the same limited area. Researchers have linked these conditions to higher risks of whale entanglement. A change in ocean temperature can therefore become a collision between wildlife conservation and fishing livelihoods. Harmful algal blooms are another concern. Certain algae thrive under warm, stratified conditions, although temperature is only one factor. Some produce toxins that accumulate in shellfish or small fish. These toxins can close beaches and fisheries and can poison sea lions, birds, and humans. El Niño does not guarantee a toxic bloom, and not every warm event produces one. Scientists monitor nutrients, winds, currents, and species composition because a dangerous bloom requires several conditions to align. The difference between a manageable anomaly and a costly disaster is not luck. It is monitoring, preparation, and timing. Buoys measure temperature beneath the surface. Satellites map the skin of the ocean. Ships sample plankton and nutrients. Tide gauges track water levels. Weather balloons and satellites observe winds and moisture. Fisheries surveys record where species are moving. Climate models estimate how the coupled system may evolve. None of these tools can remove the hazard, but they can convert an invisible change into an early warning. Now we reach the most important question. What could the United States feel next, and when? The first effects are already present along the west coast. California's coastal waters have remained unusually warm in several regions. Marine species are responding. The eastern Pacific hurricane season is active under a climate pattern that favors more activity. Elevated sea surface temperatures can support stronger storms when wind shear, moisture, and atmospheric stability are also favorable. The next phase will likely become clearer during late summer and fall. NOAA expects the offshore heat wave to continue expanding through summer, while the probability of coastal marine heat wave conditions rises, particularly off California. Scientists will watch the distance between the offshore warm pool and the coast. They will watch north to south winds because persistent upwelling could keep a cold barrier near shore. They will watch whether coastal winds relax during September and October, when offshore heat waves have often moved closer to land in previous years. They will also watch the tropical Pacific's subsurface heat. Surface temperatures can change quickly after strong wind events. A deep reservoir of warm water makes El Niño more resilient because cooling the surface does not remove the heat stored below. The July update showed a downwelling Kelvin wave and a deepened eastern thermocline. Continued westerly wind bursts could push more warm water east and strengthen the event. A return of stronger trade winds could slow that development. Keep an eye on tropical thunderstorms too. El Niño is not fully described by water temperature. Scientists want to see persistent atmospheric coupling, enhanced rainfall over the central Pacific, suppressed convection near Indonesia, and pressure and wind patterns consistent with a weakened Walker circulation. The atmosphere is what carries the Pacific signal toward North America. A warm ocean without a matching atmospheric response has less power to reshape distant weather. By autumn, attention will increasingly turn to the jet stream. A strong El Niño often strengthens the subtropical jet and directs it across the southern United States. That can increase the odds of repeated storm systems, heavy rain, mountain snow, and severe weather in some regions. Southern California, Arizona, New Mexico, Texas, and the Gulf Coast may receive more storm opportunities than normal. The northern United States may experience a milder winter on average. Parts of the Pacific Northwest and northern Rockies may lean drier. But a wet seasonal outlook does not mean steady, gentle rain. California's most damaging flood years often involve short periods of intense atmospheric river activity separated by long, dry stretches. Atmospheric rivers are narrow corridors of concentrated water vapor. When they reach mountains, the air rises, cools, and releases heavy precipitation. A strong event can produce several inches of rain in a day and rapidly raise rivers. El Niño can influence the storm track, but researchers cannot say in July exactly how many atmospheric rivers will strike, where they will land, or whether they will arrive in useful intervals or dangerous clusters. Snowpack is another uncertainty. A stormier southern track can bring valuable mountain snow, but warmer air can raise the snow level. More precipitation may fall as rain at lower elevations, increasing runoff and flood risk while reducing long-term water storage. Reservoir managers may face competing demands: capture water for drought protection, maintain space for flood control, and protect communities downstream. The same Pacific pattern can therefore relieve drought in one basin while increasing flood danger in another. Wildfire impacts are also complicated. A wetter winter can encourage vegetation growth. If the following warm season becomes dry, that additional vegetation may become fuel. In other regions, higher winter moisture can reduce fire danger. El Niño's wildfire influence varies by region and often appears months after the ocean reaches peak warmth. Claims that El Niño will simply end wildfire risk or guarantee a catastrophic fire year are not scientifically justified. For the Pacific Northwest, Alaska, and the Northern Tier, a warmer winter may reduce heating demand and severe cold outbreaks on average, but outbreaks can still occur. A seasonal average can hide dramatic short events. 10 unusually warm weeks can coexist with one dangerous Arctic blast. In the same way, a generally wetter southern winter can still contain drought intervals. Hawaii faces a different set of concerns. An active Central Pacific season raises the number of tropical systems that may develop or move through the broader basin, but it does not determine landfall. Even storms that remain offshore can produce high surf, coastal erosion, heavy rain, or dangerous marine conditions. The National Hurricane Center and Central Pacific Hurricane Center will provide the forecasts that matter once individual systems form. Coastal communities should watch tide forecasts and water level anomalies as winter approaches. El Niño-related sea level elevation can combine with seasonal king tides. A modest storm surge that would normally remain below a seawall may cross it when the background water level is higher. Roads, storm drains, parking lots, wastewater systems, and low-lying neighborhoods can flood even under clear skies. These are often called nuisance floods, but repeated saltwater intrusion can damage vehicles, foundations, electrical systems, and local local businesses. The ocean economy may feel the change before many inland residents notice anything. Fish distributions can shift within months. Salmon impacts may not become obvious until adult fish return 1 to 3 years later. Crab seasons may be delayed by toxins or entanglement concerns. Warm water species may create new opportunities in northern ports while traditional catches decline elsewhere. Managers must make decisions with incomplete information because waiting for absolute certainty can mean reacting after the ecosystem has already changed. There is also a global dimension. El Niño can affect drought and rainfall patterns across South America, Africa, Asia, and Australia. Crop yields and commodity prices can move. Supply chains can be disrupted by floods, droughts, low river levels, or storm damage. American consumers may feel a Pacific climate event through food prices or insurance costs, even if their own weather remains ordinary. These links are probabilistic and vary from one event to another, but the Pacific's reach is enormous. What would have to happen for the worst realistic U.S. outcomes? For West Coast flooding, a strong El Niño would need to coincide with a storm track aimed at California. One or more intense atmospheric rivers, saturated ground, high tides, and elevated coastal water levels. For a dangerous Pacific hurricane impact, a powerful storm would need to form and then encounter steering winds that bring it toward Hawaii, Mexico, or moisture into the southwest. For severe ecological damage, marine heat would need to persist long enough, extend deep enough, and reach biologically important coastal zones while reducing nutrient supply or changing prey quality. Those conditions are possible. They are not guaranteed. This distinction is the responsibility shield between useful warning and misinformation. Scientists cannot predict a specific California flood, Hawaiian hurricane, toxic bloom, or fisheries collapse from the July El Niño index alone. They can identify a climate background that increases certain risks and then monitor the shorter-term ingredients as they develop. The most important signals over the coming months will be updated Niño region temperatures, subsurface heat content, trade wind strength, tropical rainfall, the size and coastal distance of NEP 25A and NEP 26A, west coast upwelling winds, coastal sea level, eastern Pacific cyclone activity, and seasonal jet stream forecasts. No single map tells the whole story. A red ocean map may look frightening, while strong upwelling protects the coast. A slightly cooler surface may hide a deep reservoir of heat. An active hurricane basin may send every storm away from land. Context matters. So, has the Pacific entered a dangerous new phase? Yes, in a precise and limited sense. The tropical Pacific has moved into a strengthening El Niño. The ocean and atmosphere are now strongly coupled, and NOAA sees an 81% chance of a very strong event during the final 3 months of 2026. At the same time, 2 large marine heat waves are being tracked in the northeast Pacific, with coastal California warmth already near historical extremes for the season. That combination deserves serious attention. But the most dramatic interpretation is not supported. The Pacific is not about to explode. El Niño does not trigger earthquakes or volcanic eruptions. A marine heat wave does not guarantee a mega hurricane. The United States is not certain to experience one uniform disaster. The scientifically supported concern is smaller, slower, and in many ways more difficult. Prolonged ocean warmth can gradually load the climate system, alter ecosystems, raise coastal water levels, shift storm probabilities, and create several different hazards across different regions and times. The real danger may not arrive as one unforgettable wall of water. It may appear as repeated high tide flooding in a coastal neighborhood, a salmon season that fails 2 years later, a hurricane that intensifies over unusually warm Pacific water, an atmospheric river striking when reservoirs and rivers are already full, or a warmer winter that changes snow storage across the West. These are not cinematic guesses. They are the pathways scientists are measuring now. The next major checkpoint is NOAA's August 13th El Niño update, followed by the late summer evolution of the offshore heat wave and the peak months of the eastern and central Pacific hurricane seasons. Until then, the responsible approach is to watch the data, understand the probabilities, and prepare for regional hazards rather than assume one nationwide outcome. If you have lived through an El Niño winter, unusual coastal flooding, a damaging Pacific storm, or a major change in local fishing conditions, return to the comment section and tell us what you experienced and where it happened. Personal stories help show how one ocean pattern can affect communities in completely different ways. And if this breakdown gave you a clearer picture without the hype, press the like button and help us reach the 5,000 like goal. Subscribe and turn on notifications so you do not miss the next major update from NOAA, the National Weather Service, or the scientists tracking these heat waves. No filler, no guessing, just the facts and the full picture. Let us go. See you in the next one.